All right, so we want to factor this trinomial. Now, what makes this trinomial special is that it's got a perfect square right there, all right, and a perfect square right there. So when you're factoring trinomials, when you notice that in trinomials, you've got two perfect squares uh, that are on the as your first and your last um, elements of the trinomial. You kind of know what a plan of attack would be, and that plan is this: to since it's a trinomial and there are no common factors, you're just going to factor out the first times the first, so you got an x and an x, and then because this is a perfect square, you're just going to go along and you're going to say, okay, I'm guessing that it's going to be 11 and 11 because 121 is 11 squared. You also have a good idea that 11 and 11 is going to work because that is um, twice that. So it looks like it's going to be like that, and of course we will write that since those two factors are the same as x plus 11 squared. All right, let's try this one right here. So again, it's a trinomial. There are no common factors, and we notice that in the first and the last positions, we have something that's perfect squared. That is a 4a squared, and this is a 3 squared. So that should lead to this kind of factorization using a 4a and a 4a. Now, of course, we in the first and the first positions, we could have several choices, right? You could have 4 and a 4, you could have 2 and an 8, or 1 and an 8, 1 and a 16. That's how you get 16. But again, with this certain pattern that we're looking at, where the first and the last are both squares, we want to try the perfect square. And a 9 is either a 3 squared or a minus 3 squared. And probably we're going to go with a minus 3 because this is negative. And notice when you FOIL this out, that's a minus 12a and a minus 12a. So that gives you your minus 24a. All right, and so we'll write that as a 4a minus 3 squared. All right, let's look at this one here. We don't see any perfect squares here, right? 2 is not a perfect square, 98 is not a perfect square, but that's not even where we start. We first notice that we can factor a 2 as a common factor out of everything. And now we look at it and notice, hey, that is a n squared is an n squared, and 49 is a 7 squared. So it looks like now we can factor this into n minus 7 and n minus 7. So 2 times n minus 7 squared. All right, let's do this one. This one looks quite a bit more complex, but if we notice, we've got perfect squares in the first and the last positions. 25x squared is a 5x squared, or 5x squared, and 36y squared is a 6y squared. So everything is squared, so it looks like we can go 5x and a 5x. That gives us our 25x squared. And if we try a minus 6y and a minus 6y, that gives us our plus 36x, or 36y squared. And notice when we do the outer, here it's a minus 30xy, and here is another minus 30xy, so a total of minus 60xy. But there it is. And these are called perfect square trinomials, because when you factor them, you end up factoring them into the same two factors, so you can write them as something squared.